Welcome to Daily Papers. Today, we're looking at a paper that tries to solve a problem you've probably experienced yourself. You ask an AI chatbot a question, and you can almost see the gears turning as it types out the answer one word at a time.
Right. It can feel surprisingly slow for something so advanced, and that slowness is a huge bottleneck. Large language models, or LLMs, are incredibly powerful, but they are also incredibly expensive and energy intensive to run. This paper argues that the core of that inefficiency is the very thing you just described, the one word at a time process.
Right. The paper is called Continuous Autoregressive Language Models, and it proposes a radical change to how these models generate text. The authors basically say, what if, instead of thinking in single words, we could teach the AI to think in entire phrases or chunks of text at once?
So let's break down how an LLM like ChatGPT normally works. Its fundamental task is next token prediction. A token is basically a word or a piece of a word. If you give it the sentence, "the cat sat on the," its only job is to predict the single most likely next token, which is probably Matt. Then it adds Matt to the sentence and does the whole process again to predict the next token after that.
It's an incredibly simple process, repeated over and over. But that simplicity is the problem. The model is using its immense brain power to make a tiny, low-information prediction each time. The paper compares this to trying to unlock the next order of magnitude in efficiency. They argue that we've hit a wall with the one token at a time approach.
So this is where their new idea called CALM comes in. That's CALM for Continuous Autoregressive Language Models. The big idea is to shift from predicting discrete tokens to predicting continuous vectors.
Okay, discrete versus continuous. Let's unpack that. Discrete means you're picking from a fixed list, like words in a dictionary. The model looks at its vocabulary of, say, 50,000 tokens and picks one. There are no options in between.
But continuous is different. Imagine a map. A discrete location might be Paris or London. A continuous location is a specific set of coordinates, like latitude and longitude. You can have infinite points in between. A vector is just that, a list of numbers, like a coordinate in a high-dimensional space of meaning.
And here's the genius of the CALM system. It doesn't just represent one token with a vector, it takes a whole chunk of tokens. Let's say k equals 4, so a phrase like sat on the mat, and uses a special tool to compress that entire phrase into a single dense vector.
This tool is called an autoencoder. It has two parts that work together. The encoder part does the squishing. It takes the 4 tokens and converts them into one dense vector. And the decoder part does the unsquishing. It can take that vector and reconstruct the original 4 tokens, sat on the mat, with over 99.9% accuracy.
So the LLM's job is no longer to predict on after sat, then the after on, and so on. Its new job is just to predict the single vector that represents the next chunk of 4 words. This means for every one step the CALM model takes, a traditional model would have to take 4.
It's a huge leap in efficiency. The paper calls this increasing the semantic bandwidth of each generative step. Instead of sending a tiny packet of information, one word at each step, you're sending a big one packed with the meaning of 4 words. This directly reduces the number of steps the model needs to take, making it fundamentally faster and cheaper to run.
Of course, this paradigm shift creates a whole new set of challenges. For starters, how do you teach a model to predict a vector in an infinite continuous space? The old method of picking a word from a list just doesn't apply.
The researchers had to develop a whole new modeling toolkit. They call it an likelihood-free framework. In simple terms, they don't bother trying to calculate the probability of every possible vector. Instead, they use a clever training method based on something called the energy score, which essentially teaches the model to generate vectors that are close to the correct ones without needing to do all the impossible math.
Another challenge was evaluation. How do you grade a model like this? The standard report card for LLMs, a metric called perplexity, is based on those probabilities that the CALM model doesn't even calculate.
So they invented a new metric called Briar limb. It's a really neat likelihood-free way to measure performance. It works by just taking samples from the model and checking how good its guesses are. And they showed that this new Briar-Limb score lines up almost perfectly with the old perplexity metric, proving it's a reliable replacement.
So the big question, did it actually work?
It did, and really well. Their experiments show that calm models can achieve performance comparable to traditional models, but at a significantly lower computational cost. For example, one of their medium-sized calm models performed about as well as a standard small model, but it required 44% fewer computational resources for training and was 34% faster at generating text.
Those are really significant gains. It's not just a small improvement, it's a new path forward. It suggests a new way to scale AI models, not just by throwing more data and more computers at them, but by making each step they take more meaningful and efficient.
And what's really cool is that this introduces a new lever to pull. You can choose your chunk size, K. A bigger K means faster generation, but it's also a harder prediction task for the model. So you can trade off between speed and performance to find the perfect balance for your needs.
So this paper fundamentally reframes the task of a language model. It's a shift away from the slow, step-by-step process of predicting single words towards a much more efficient paradigm of predicting entire concepts or phrases, all bundled up into neat little packages of numbers called vectors.
It's a powerful idea that could lead to ultra-efficient language models that are more accessible, affordable, and sustainable. A very calm and collected approach to a chaotic problem.